בסדר? רק שיחה. אוקיי. אהרון, אתה שומע אותנו? אהרון?
Can you see and hear? Okay. Okay, Aaron, good to hear you. I cannot see you, but good to hear you. So we're going to start soon with do you see also you see the PowerPoint over there? Clear? And do you see also the public? Okay, good. Is Nurit Stober over there is waving to you, and she is the second. She's the second examiner, evaluator. So the rest of the audience you see, they are students at the Department of Marine Geosciences and some friends of Yakufo, I think. So thank you, Aaron. For you guys, online is the Professor Aaron Michele from the University of Malta. Okay? He's a geomorphologist, marine geomorphologist, and geophysicist. Right, Aaron? Okay, good. So you guys, you know who is in the other side. Okay, so the issue goes like that. We're going to listen to Yakufu's thesis defense, and then you start to if you have questions, you ask. Also the audience, not only the evaluators, and then eventually Yakufu will go out, and but you also go out. No, wait a minute. Yeah, eventually they go out. I mean, they can ask questions if they want to, although probably you would not like them anymore. But so they ask questions, they go out, eat the food outside. The examiners ask more questions, and then eventually you go out, and we are discussing your grade. Okay? And then after the grade is discussed, you come in, and then we tell you how is it. Okay? So this is the way it goes. Try not to ask questions in the middle unless Yakufu wants. Do you want? Okay. So yeah, so ask the question afterwards. Okay. So Yakufu, the podium is yours. I don't know. You maybe will use this one. Can you use this one?
So thank you, everyone. Now I am defending my thesis. It's about 3D seismic geomorphological analysis of submarine channels in the Paleocene succession of the Levant Basin. This research is supervised by Dr. Nicholas Waldman. As we know, marine sediments are very important and the most significant sediment deposition system in the world. It um, it starts from the continental shelf as a submarine canyon and submarine valleys until the continental rise. In the slope, it also included some mass transport depositions and landslides. But in the deep ocean, it always occupied by deep marine submarine channels. Submarine channels. In the study, I will focus on the submarine channels that in the deep located in the deep basin. In seismic cross sections, submarine channels always shows us like this type galley wing geometries, and the high amplitude reflections always can be found at the bottom of the submarine channel, which is generated from the sharp lithological changes. And the coastal sediments deposited on the bottom of the submarine channel, while the finer sediment deposited on the flank to form the channel levee. Channel levee always downlaps the underlying submarine underlying depositions, and in the seismic section, it always ranges from the low amplitude to high amplitude. Except the cross-section analysis of submarine channel, we also use plan view map of submarine channels to investigate them. In this map, we can see very well-developed submarine channel and a meander loop here. We can investigate them from all kind of aspects, even they are buried under the deposits. The submarine channels are very well studied in the world, and there is a short summary of all the submarine channels in the world. Um, as we can see from the map, the submarine channels, well-studied submarine channels, they are located near the area of big rivers, including the Gulf of Mexico, and there is a river of Mississippi, the South America and Amazon River here. Also, the West Africa and the Bengal of Van. These places have big rivers, and then they formed the big delta as well as submarine channels. So what about the Levant Basin? As we know, the longest river in the world, the Nile River, enters to the Mediterranean Sea, just the southeastern side of the Levant Basin. Not exceptionally, if you look at the submarine channels identified from the Nile Deep Sea Fan area, there's a lot of submarine channels, and then in here, this submarine channels is highlighted by green color. These submarine channels identified in the Levant Basin. And then let's look at the bathymetry map of the Levant Basin. In here, we can see that there's a bunch of submarine channels very well developed, and then all of them are northwest directed. This map is generated from the 3D seismic data. In here, we can see a submarine channel very well developed also. All of the seafloor submarine channels in the Mediterranean Sea, including the Levant Basin, is very well studied in aspects of the architectural elements and their interaction between the subsurface deformations. However, there is still some questions not answered yet. These questions included how the submarine channels developed through time in the Levant Basin, and their development is a response to the changes in the depositional environment or not. In this study, I will try to fill this knowledge gap. Why I have to fill these knowledge gaps? Because submarine channels is not only is a very important conduit for sediment transport to the deep basin. They not only shape and change the nature of the seafloor, but also records the climatic information from the source area. Also, submarine channels is very important for the geohazard prediction and the prevention, because when the submarine channel is active, they can destroy or damage the seafloor infrastructures. The last but not the least is that submarine channels can be important hydrocarbon reservoirs. There is 43 turbidity reservoirs. Turbidity reservoirs that discovered in the world. These reservoirs also including some submarine channel reservoirs. To achieve this goal, I will identify and map the submarine channels in the Pliocene interval of Levant Basin, and then I characterize, also classify the submarine channels based on their section view and the plan view geomorphologies. And then I identify the channel filling seismic phases, and then estimate the age and that constrains the elements that can contribute the development of submarine channels in the Levant Basin. At the last, I will try to understand the evolution of submarine channel in light of sea level fluctuations. The Levant Basin is located in the easternmost part of Mediterranean Sea. It's a post-rift basin. As from the cross-section, we can see that its rifting stage ranges from the Paleozoic to early Mesozoic. At that time, a series of forest and the garden system were formed. After that, this basin entered the post-rift stage. In the late Cretaceous, the African plate and Arabian plate converged with the Eurasian plate to form the famous Syrian arc. In the late Miocene, the Mediterranean Sea disconnected with the Atlantic Ocean, and a thick layer of evaporites deposited in the whole Mediterranean Sea. In the beginning, from the beginning of the Pliocene, the Mediterranean Sea is reconnected with the Atlantic Ocean, Also, at the same time, the modern Nile Delta formed here, and it becomes the most important sediment source to the Levant Basin. In this study, I will use two types of data. The first is 3D seismic high-resolution data, which is located 50 kilometers offshore central Israel, and it covers about 13,000 square kilometers. The data is press-tag migrated and have a high resolution with 6 meters. Another kind of data is well log data from the Mira-1 well, which mainly consists of gamma ray data, and the resolution is 15 centimeter. For the interpretation of seismic data, I use the classical interpretation method, including horizon picking, surface mapping, and slicing. For the slice, I also use two different kinds of methods. If the horizons are parallel and they are horizontal, I use the depth slices. If the horizons are not parallel and dipping in different in different angle, I use the stratal slices. In this way, I can identify and map the geomorphological features within these two reference horizons. Except the classical method, I also use some seismic attribute analysis, including amplitude extraction and RMS, root mean square amplitude extraction. This two method is very useful to identify the different deposition elements, because these elements have a different acoustic impedance comparing to the sediments surrounding them. For the geomorphological analysis of submarine channels, I used both plan view and the section view map. In the plan view map, I measured the straight length of submarine channel and the sinus length. The straight length is the length that is a segment length begins from the beginning of the channel until the ending of the channel, while the sinus length is a length that along the channel axis. And the sinusity is calculated as a ratio of sinus length to the straight length. The channel depth and the channel width is measured every 500 meters and averaged. All the parameters are used to classify and to describe the submarine channels identified in the Levant Basin. The gamma ray is used as a proxy to the grain size. When the gamma ray is a boxcar shape, it shows that the sediments are the same size. If it's a funnel shape, it shows the sediments are become coursing, or the grain size is increasing towards up. If it's bell shape, it shows the sediments are become fining. If it's bow shape, it's combination of the funnel and the bell shape. So let's look at the cross section. First, I interpret some faults, main faults in the region. After that, the main very obvious horizon, high amplitude positive reflection, and with distinctive topography on the bottom is interpreted as the top of the erosional surface of Messinian evaporites. And the unit below it, below the horizon, is named seismic unit 1. Another very obvious horizon on the top is also high amplitude positive reflection, which is interpreted as a present seafloor. On the framework of this two interpreted horizon, I divide the whole seismic section into 4 seismic units. Just opposite unit SU seismic unit 1 is seismic unit 2A, which is consists of low amplitude continuous parallel to subparallel reflections. Above this unit is seismic unit 2B, which consists of high amplitude subparallel to parallel and discontinuous to continuous reflections. If we closer look at this seismic unit, we can see that the reflections in this unit is disturbed or cut by some troughs. And then in the later slides, I will show that these troughs are interpreted as a submarine channels. But there is a horizon that very low amplitude, and then it can be traceable all over the section. Without any changes in the thickness. It's covering the sediments below it, and in here we can see a submarine channel, and then it's filling or draping all over the truncations in other sections. So this horizon will divide this seismic unit into two subunits. And then I divide this unit to seismic unit 2B1 and then 2B2. Above this unit, seismic unit 2B is another low amplitude parallel to subparallel reflections. This is unit 2C, and above it is seismic unit 2D, which is bonded at the top by the modern seafloor, and also a present submarine channel is interpreted here. Also, between the seismic unit 2C and the 2D, there is another chaotic and a very transparent unit interpreted as a mass transport deposition. In this study, I will focus on this unit. Other units above and below, there is no submarine channels identified, but only in this seismic unit 2B, there is many truncations or many incised channels interpreted. There is a short summary of the submarine of the seismic units. The seismic real-time map shows that in the lower part of each seismic unit, the gamma ray is decreasing, while in the upper part, the gamma ray is increasing. It shows that the lower part of each subunit, the grain size is increasing, while the upper part grain size is decreasing. From the thickness map, I can see that they have the same thickness, ranges from 30 meters to 120 meters. Also, the upper unit have a more northeast progression of sediments. If we look at the amplitude map extracted from the 10 meters below of Horizon C, we can see there's a very well-developed submarine channel here, also some faults. And then let's look at the combination map of the cross-section from here and a depth slice from here. Here also very well-developed submarine channel, here, and this is also submarine channel. And also a fault comes this way. After interpreted, this submarine channel is displaced by this strike slip fault and offset about 200 meters. That means the submarine channel developed before the fault. Interestingly, the top of the upper layer of each subunit is dominated by U-shaped channel. We can see from here it's U-shape, and here also U-shape. But the lower part of each subunit is dominated have the same direction towards the northwest. However, they are different in the number. The number of submarine channels identified from the lower part is half of the submarine channels identified from the upper part. And then I tried to use a statistical method. And then I find that the submarine channels identified from the lower part is small in numbers, about 10 or 12. and then they shows a V-shape or asymmetrically U-shaped, but it's considered as a V-shape. And also, they are very narrow, about 120 meters in width, and their depth is only 20 meters, about 20 meters. Most importantly, their average sinuosity is very small, and then I can consider them as straight channels. But the submarine channels from the upper part, they are more in numbers, as twice as the lower one, and they are U-shaped. Their average depth and the width is much more larger than submarine channels in the lower part. Also, their sinuosity is larger, and then also I can identify them, consider them as a sinus channel. So in this way, from the filling shape description and the geomorphological parameters, I classify the submarine channels into two types. The submarine channels in the lower part of each subunit, and the type 2 submarine channel is the upper part of each subunit. And then let's look at the seismic phases of each submarine channel. In here, we can see that the submarine channel, type 1 submarine channel, they have a little bit simple configuration, and it shows convex upward filling. However, the type 2 channels, they have much complex infilling system, but mostly they are concave upward fillet or shingled fillet or flat fillet with a well-developed levee system. Let's look at the submarine channel, the type 1 submarine channel. It's first, from the cross section, we can see it's V shape, okay, and then also it's concave, convex upward fillet. In the RMS map, we can see that this submarine, inside the submarine channel, they have a higher RMS value. It shows that the sediments infilling the submarine channel is coarser or have a higher acoustic impedance than the surrounding material. Also, there's a small, maybe it's overspilling. Let's look at the type 2 channel. Type 2 channel is U-shaped, and also a high amplitude reflection is identified from the below. This channel also cut by the fault. Again, type 2 channel. This channel have very good meandering shape. From the depth slice, we can see that this is last stage channel. However, this is abundant channel. If we see the cross section, we can see that there's it filled with a low amplitude stuff, and then it's also like concave upward filling. Another type 2 channel, from the depth slice, we can see this channel is very well developed through time, and then it changes the roots. From the cross section, we can see that this area is represents the different submarine channel in the different stages, and all are shingled or dipped towards the last channel filling. Last channel also shows a little bit concave upward filling. So, if we summarize the submarine channels identified in the Paleocene succession of the Levant Basin, type 1 channel, they are located in the lower part of each subunit. And as we see, the lower part of each unit, it shows its coursing upward trend. And the channels in this part is V-shaped. They are narrow, they are straight, and always showing convex upward filling. They have no migration and no levels. But the submarine channels identified the upper part of each subunit, where the gamma ray increases. This submarine channel have these submarine channels are U-shaped, wide, and they have higher sinuosity. They have a concave upward fillet and migrated. Also, they have levees. So the question comes: what these different kind of submarine channels stands for. As we can see from the classic model of turbidite system, there's mud-ridge system. It's very large, and as they have very few content, very small sand content. And the Lavid migrated sinus channel is the main architectural element of this system. However, the sand-rich system, they are very smaller and they consist of more than 70% of sand. Their deposition depends on the high density turbidity currents, which forms relatively small and straight sandy channels. In here, we can link the type 2 channel to sandy, type 2 channel to the mud-rich system, type 1 channel to the sand-rich, or at least type 1 channel to the mixed system. They are in type 2 is most likely to this system, but type 1 channel is this or a mixed system. Also, if we see from the filling pattern, if a channel is filled with coarser material, when it compacts, it's hard to compact the submarine channel in the center because there are harder material inside the channel, but in the flanks there are small amount of coarser material. So it always shows a convex upward filling. If the submarine channel is filled with muddy material, when it compacted, it's easier to compact the center of the submarine channel, and then it shows as a concave upward filling. In our study, this concave convex upward filling channel is identified as a type 1 channel, and then this one is type 2 channel. Also, we can see from the literature that the V-shaped channel are formed by strong down-cutting erosion. However, the U-shaped channel are characterized by a fine-grained sediment supply, indicating formed by lower density flow. So in here, I can infer that the type 1 channel is formed by higher density flow, and they have a higher sand to mud ratio. While the type 2 channel, they developed by the lower density flow, and they have lower sand to mud ratio. If you look at the column, we have submarine channels identified from the seismic unit 2B, but not 2A and 2C. We have submarine channels. If we closer look at this unit, we will find that the lower part is dominated by type 1 channel, while the upper part is dominated by type 2 channel, while they are cyclic. As we know, the development of submarine channel is controlled by these three elements: climate, sea level, and the tectonic. Climate affects the amount of sediment supply, and also they can modify the weathering, the efficiency of weathering, erosion, and the transportation process in the interland. But sea level can affect the development of submarine channel in a more direct way. They can exposure or merge, connect or disconnect the continental shelf to the deep basin. While the tectonic, they can affect in the large scale. They will control the geometry, size, and the morphology of the basin. As I know from the literature, the global tectonic event in the Pliocene to Miocene, from the Miocene is negligible. Also in our area, we don't have very significant tectonic events. Also, as we can see from the submarine channels that displaced by the fault, it shows that even the local tectonic events, the salt tectonic, cannot affect the development of submarine channel. In here, the tectonic and the climate not only can affect the sea level, but also they affect to each other. And also there's another classic model shows that when the sea level higher than normal and then it's still rising, the deep basin is dominated by hemipelagic sediments. when the sea level goes down, the turbidity, the density of turbidity currents, and also the sand to mud ratio is increasing in the deep basin. While the sea level is rising until the normal sea level, the density of turbidity currents is decreasing, as well as the sand mud ratio in the turbidites. After that, the hemipelagic condition were built again. So in here, I can say, or I think the type 1 channel is developed during the falling stage, while the type 2 channel is development formed in the rising stage. However, the question comes: do we have the relative sea level cycle in our study area? If we look at the sea level curve, in here the sea level is in the time domain, while the sections I interpret here, they are in the depth domain. They are not matching like that. And then it looks like there's many cycles, but after I smooth the sea level curve, calculate from the oxygen isotope, we can see less cycles than that. In here, the age of the top erosional surface is widely accepted, is 5.3 million years ago. And but the age in the top is not very confirmed, but it's widely accepted, or in some reports, as they said, the base or top of the empty mass transport deposition is about 2.7 million years. Because the mass transport deposition is very fast, and it's like an event, we can see, you can say, it will not change a lot in this timetable, because it's a millennium time scale, and then the mass transport deposition is very fast. In here, we can see this our study unit from horizon A to horizon C is located somewhere here, from this TES from 5.33 to 2.7, but it wouldn't be here. Why? Because it's widely accepted that the submarine channels develop when the sea level falls. Because when the sea level falls, the shelf is exposed, and then the canyons or rivers can extend to the deep ocean. So I assume that my study area from horizon A to C is located somewhere here. There's a big sea level fall before the 2.7, and also there's cycles, but it's very tricky to say which cycle corresponds to A to B and which cycle links to B to C. Also, the sediment supplied from the Nile reached its peak in the mid-Pliocene in this time, and this increased sediment supply is attributed to the humid African climate during that time. So, considering the estimated age, I can see that the submarine channel development is contribute to the climate in the long term, but also to the sea level fluctuations in the short term. Based on this information, I established a model. When the sea level, relative sea level higher, we have pelagic sediments in my study area, and then there's hemipelagic sediments, and then no channel identified here. After that, we have a relative sea level falling. There is a V-shaped sandy submarine channel developed. After that, the sea level start to rise, and then a U-shape, a muddy, and a sinus submarine channel developed. After that, the sea level goes its relative higher stage, and then we have another horizon B, which is very continuous and without any changes in the thickness, is deposited in here. After that, we entered another cycle. We have type 1 channel. It's also V-shaped, sandy, and very straight. After that, we have the sea level rising, and then the U-shaped channel developed. After this, the sea level rise to relatively higher position, and then we have this seismic unit 2C deposited. Also in here, no channels are identified. So if I conclude, a channelized unit was identified within the Pliocene secession of the Levant Basin, and this unit furtherly divided into two different subunits. The lower parts of each subunit is dominated by type 1 channel, and here the gamma ray is decreases. The upper part of each subunit shows a finding upward trend, and they dominate by type 2 channel with lower sand to mud ratio. Considering the age of the unit, I assume that the long-term development of the submarine channel are linked to the increased sedimentation rate result from the humidity period in East Africa, and also that associated with the falling stage of sea level. The cyclic appearance of two different types of submarine channels is interpreted here as a result of sea level fluctuations in the millennium scale. In the future work, if there's enough time and funding, I will try to extend the study area to the whole Levant Basin and identify, map all of the submarine channels in the Pliocene, and then compare them to submarine channels in the present sea level to understand the long-term evolution of submarine channels in the basin scale. Also, for the future study, the accurate age is very important, and the need to improve the certainty of the model, because the high resolution age control can give us the right sea level cycle in the study area. Also, I will try to model and calculate the volume of sediment in the channel. This will be provide an very important information about the hydrocarbon or fluids preserved in the V-shaped sandy channels. In this study, thanks to ILDC, Modern Energy, and the GGR for permitting me to publish the geophysical data set. I also thank my professor, Dr. Nicholas Waldman, to accept me a master's student and his supervision during the study. I also very grateful to Dr. Obialik and Emmanuel for fruitful discussion during the study. And the many thanks to Schlumberger Paradigm and the Kingdom Softwares. I also express my thanks to the Department of Marine Geoscience for funding me in the study. I am very grateful to my family and the friends who are always been supporting me during my study. So thank you all, and if you have any questions.
Okay, thank you very much, Akufu. A good presentation. Somebody has questions to ask him? Or
it's okay. So, what do you think is the commonality between this late early Pliocene, early late Pliocene phase, which generate these channels, and the late Pliocene channel phase? The phase you've been working on and the modern phase where we get channels again. What's the commonality?
The modern channels are Okay, here we have submarine channels in this study area and in this area. Uh, the study shows that these modern sea level channels is always linked to the climate change and the sea level fluctuations. And, and they also consider the amplitude and the frequency of sea level fluctuation, and they try to link these submarine channels into these sea level fluctuations. But the paleo submarine channels, they can form in the lower sea level stage, but the frequency and the amplitude is not as big as the present. That's maybe because they actually act like that, or maybe we don't have enough data or from the resolution. So this is more linked to the very sea level fluctuation, but in the paleo submarine channel, they link to the sea level fluctuation also to the climate. It's difficult to say because we don't have the very correct age. We don't know which age this study unit located.
Okay. Okay, so now the jury basically is going to stay and ask the questions. So thank you very much for everybody. And you have the cookies.
Just to congratulate you for, you hear me? To congratulate you for the overall presenting of the thesis and for your presentation today. Thank you. Tuk tuk. Aaron. Aaron, hello.
Hello there. I'm still here. Hello, Louis.
Okay.
I couldn't see you earlier.
You are watching us? That's good. Okay.
Yes, still here. Still here.
Okay. Okay. I hope that you hear all the presentation. I think we need to look over there. Yeah. You're inside that machine. Okay. Okay. Good to hear you, Aaron. So why do we do that? So basically, just so both of you know, you are basically giving now grade. Well, you're going to ask questions, and eventually it's going to go out, and we're going to discuss a grade for the presentation only. The book that you already saw, I guess you have it over there too, right? So there is a grade for that thing, and he already did courses, and he has the grade for the courses. Eventually, the courses is 30%, the defense is 30%, and the thesis is 40%. But that's not necessarily you need to deal with that, just to know that you are actually doing a grade for the presentation itself. Okay? So that's for the logistics. Now, who want to start? I don't know, apparently. Okay.
First, how are you? How do you feel? Wow. You better? You feel better? Good. Good. Now, shh. Okay. Good. Okay, Aaron,
Alright.
please start.
So I won't be very mean. I found both the text and the presentation very, very good. So I only have a few questions that I wanted to ask Yakubu, who I wanted to congratulate for all of this. And I go one by one. I started the methodology actually.
Yeah.
And I wanted to ask you, how did you manage to correlate the seismics with the well data? Because from what I understand, the well data that you have are the gamma ray logs and the depth, and nothing else. Is that correct, or did I get something wrong?
Our gamma ray is also they have the depths. Our the seismic data is also depths migrated. They're already depths, and then it's matched very well.
Okay.
They are both in depth, so it's not very difficult to correlate the seismic to the gamma ray random data.
All right. But you don't have age information, right, from the borehole? Correct.
Yes, we don't have age control for
Okay.
this.
All right. And when you were correcting, like distinguishing between the mud-rich system and the sand-rich systems, not only sand-rich turbidite systems also have more lobes than mud-rich systems. And I wanted to ask you whether you see any of these lobes in your data that could corroborate your model even more.
That's a good question. Yeah, it's not always like the sandwich system as a V shape is always showing a convex upward, but not always. Sometimes it shows, but shows concave upward. So I assume, or I think this is more in the more sandy environment, or at least in the mixed with sand rich and the mud rich. Maybe they are in the mixed system, but not in the mud. But in the mud rich system, the submarine channels is very, it's very, first, it's very large. And our submarine, my submarine channels in the upper part, in the type 2 kind of submarine channels is very, they are deeper, they're wide, and it shows that, it indicates that the submarine channels can go much further, just like in the mud-rich system. And also they have very good meandering, sinuosity is higher. Also they have a levee system. And this is as characteristics of the submarine channels in the mud-rich system. So that's why I assume this type 2 channel as a sandwich, as a mud-rich system, but the type 1 channel is sandwich or a little bit mixed mud-rich to sandwich system.
And would you have any idea of why you have many more type 2 channels than type 1 in both cases?
Yes, you are right. Also, I also think about this, but my explanation is in the mud-rich system. The hydrodynamic condition is not so strong, and then the submarine channel can have many branches, or if they encounter any other kind of small topography high, they will divide into two. But the type 1 channel, because they are more erosive, they have a stronger density currents, they can cut these obstacles and still can be one. So that's my explanation to this difference in the numbers. And also the submarine channels in the mud-rich system, it's like main architectural elements that uh, forms the mud-rich system. But in the sand-rich system, the submarine channels is also very few in numbers.
All right. And if I remember well in your thesis, you mentioned potential tectonic activity that could have played a role in submarine channel evolution. And specifically, you refer to the Ethiopian uplift. Now, can I ask you why you excluded that as a potential player in submarine channel evolution?
The uplift of the, okay, when I consider the tectonic activity, I just consider the tectonic activity that can affect the submarine channels in Levant Basin. But if I say the tectonic activity in the Ethiopian plate, it can affect the submarine channel through the sediment supply and the efficiency of weathering, erosion. This is a climate side. You are right in the Ethiopian uplifting can be contribute the development of submarine channel in the Levant Basin, but it's very too far, and then it's not very direct way to impact the development of submarine channel. So in here, I didn't mention it.
All right. And just one last question, also related to this topic, because then you favor more the climatic influence in this model.
Mhm.
And I wanted to ask you, because I'm ignorant about the topic, if there's high resolution information on climatic changes in northeastern Africa that could be correlated with what you see offshore, that could perhaps corroborate even more the model that you propose. Because like in the presentation and the text, you perhaps refer to some climatic activity in the late Pliocene, which is fine, but is there something of a finer temporal resolution that you can use to associate the two?
Yes, at first I also put insolation curve from the Miocene until now. It shows in the late Pliocene we have peak. Also in the Pleistocene, in the late Pleistocene, we also have a peak. I tried to do this, but it's how to say it's very widely accepted that the sea level is actually the most important factor that controls the submarine channel. It can shift the location of the shoreline in the towards the land or towards the basin. So, but the climate change, it's uh, it's very tricky uh, because 2.7 we will start the northern hemisphere glaciation, but it's still a little bit far to my study area. It's this Levant Basin about uh, 33 degree in the latitude. I don't know how the climate change or the glaciation or this stuff can impact the development of submarine channel. So in here, I just very roughly mentioned the sediment increased sediment rate in, resulted from the climate change the in the Africa, but not the global insulation or other climatic impact.
Okay. Thank you very much. Those were my questions.
Thank you so much.
Thank you, Aaron. Nurit?
Yes. Well, several questions Aaron already asked. I made some remarks on your paper. I will tell you later on the file. My main question was about the monsoon impact. I'm not sure that to link them between the monsoon and the formation of those canyons. And I would soften somehow the statements because there can be many other mechanisms of formation, including tectonics or whatever happened. You can raise 1 or 2 meters seafloor and you'll get a different slope angle and you can start formation of a new canyon. So what I'm trying to say is maybe you can soften the statement about the impact of the monsoon. Maybe. I don't know if you can do something about it now. What else? The mechanism of formation is light, several triggers, I wrote it. And something about the resolution of, of, um, of the cross section. You mentioned the dimensions of the canyon. You point out several meters. Yes, the differences are several meters.
Yes.
So you're positive that these are the dimensions following the resolution was good enough to measure several meters here and there?
This resolution is horizontal and the vertical is 6 meter in the seismic section.
6 meters.
6 meter, yes. So, so everything, maybe I will not identify everything because some of the channels may be much smaller than 6 meter. Yes, that is right. That's right. But I checked again and again to identify every submarine channels with each layers. Actually,
Oh, I just wanted to mention that I love this painting. I also wrote it here, page, I can remember. I love it because you made all those paintings.
thank you.
Very helpful.
The submarine channels. Actually, this submarine channel identified from this layer is not actually only from this layer. It's from this horizon to here, like many slices in this, there, and then it become one submarine channel identified from the lower part. For the upper part, the submarine channel is from here to here. It's many slices, and then they combine to the submarine channels identified from the upper part. Also, the same method to the upper subunit. So the channels is not neglect or every submarine channel I can see is identified. But if there's something under the resolution,
Yes,
it's,
understood. Okay, I think that is all.
I will actually ask you a question continuing with Aaron's remark. How far with the Ethiopian plateau uplift, actually? Is a good question, actually. But my question is how far you expect, let's say that you are not in the Nile, okay? You are in the Amazon, okay? And how far from whatever uplift, let's say like that, do you expect to see an increase in channels in the deep ocean in front of the Amazons? If there is a change in the uplift of the Andes, which is something like, I don't know, several thousand kilometers away. So what is the distance that's my question.
it depends on it depends on how the uplift, the erosion from the uplift can contribute or transport to the ocean. If we have the uplift in the Northeast Africa, and our Nile system is the drainage basin is including the Ethiopian plateau, and then the increasing in the sediment can contribute the slope deposition, and then it will become unstable, become a landslide or canyons to become submarine channels. If it's too far, like it's in the South Africa, and then we have submarine channels in the Levant, maybe it's not linked because of the distance also from the drainage system. But also, if the uplift can, if the uplift can impact the sea level change or the climate in the larger scale, it also can impact or control or influence the submarine channel development.
Okay. Aaron, do you have more questions? Nurit? Okay, so
Not something that you can do much about it within
No.
this way.
okay, Yakufu, go and check if the cookies are still there.
Okay.
Well, we need to discuss. But come, you will stay outside. I need to call you. Okay, now he's outside. Okay. Aaron, what you had perfect questions actually. What do you think? Okay, let's do like that, Aaron. You are, and actually
For the
you,
presentation, we have to give you
yeah, you are both of you. You are not familiar with the grades here, basically. Well, you,
percentage.
yeah.
Okay.
It's between 0 and 100, in which basically the minimum, like really minimum, it will be 60.
Not really minimum.
Like no, like 60 will be like that guy did a favor to talk, and that the work is totally disgusting. 60 until 70. Actually, I need to do some kind of.
Give him and Mark for his presentation right
Yeah,
now?
yeah, for the presentation. Also for the book. I don't know how much you gave.
For
I
the
don't.
presentation and for the
No, for the presentation. Now it's for the presentation.
100. Really?
Well, I don't believe in the 100. 100 is not even Einstein, but this is me. I don't know you. I don't.
I would say 9, let's say, for the presentation, but it's not very good.
Very good. But 97.
So let me get it. We need to make one grade.
All right, so,
So you-
95 then?
95, 94, 94. Yeah.
94?
95 for the presentation.
Okay, the book. I don't know how much you gave
For the
actually.
book,
No, I don't need the information right now. You need to send that paper
okay.
to the secretary. They send you a paper, right? Or I did.
No, they said
I still have it, but I haven't sent it because I thought I would include something from this presentation, but if not, I can send it right after we finish.
Okay. Okay. And for that thing, also you need to give a grade.
Yes.
Okay.
for the thesis itself.
What is the thesis? For all the
Thesis,
things.
the book, this.
For the book, you did.
This is the book?
Yeah, that book.
That's
You need to
the
give a grade for that book.
Ah, okay.
Yeah.
For that I would.
Don't tell me now. It's not
Okay.
urgent. You need to send that to the secretary.
Okay.
The evaluation thing.
Okay.
Okay, and over there is a space in which you put the grade.
Okay.
Okay. This thesis was sent already, and it's under review in marine geology.
Good luck. You're one of the authors?
Yeah,
Yeah.
maybe reviewers. I don't know. But it was sent actually a month ago already, so it's deep in review now. But in general, what do you think? I don't know.
Sometimes.
Okay.
Exactly.
Yeah.
This is also my opinion.
Yeah, you're totally correct that the tectonic. Less supported, but your comment actually is perfect. Okay. Doctorate actually. You want?
Nicely. You wrote the book. The book is very nicely written, and yeah, and I love that the drawings, and it's very precise. I really enjoyed reading it. It was, in my opinion, it was a really good one comparing to others that I saw, that I read.
Yes.
So yeah, I want to continue a doctorate, and I have several options for him. I'm trying to do. There is some kind of an MOU between Haifa and the University of Texas, Texas A&M, but in oceanography. So it means the contact I have is in IODT stuff. So I'm trying to build it up. In one way or the other, if it's going to be built up, it's going to be in October 2018. The good thing is that they put a lot of money. I have small stuff or whatever, but Aaron, we have a student here in hand if you are interested.
That's great. Yeah, maybe we can do something together on a 3D, because he's already used to 3D seismic.
Yeah,
Maybe something on
Yeah,
3D seismic geomorphometry or something like that,
Yeah,
which is
yeah,
something I always wanted to do.
yeah. So maybe we can talk about it in a month. We are meeting.
Yes, exactly.
Yeah. For the meanwhile, I have like a small project that is doing organic matter. I have a project that somebody needs to do it, so he's
All
doing
right.
it. But in a month, I mean, if you actually, we need to talk about other things as well, you know.
Yes.
But
And we need to run. Remember, we need to run as well.
yeah, and we need to run. So I hope that we will have time actually to talk.
Yes.
And you. Yeah, good. Like
sure.
1 hour, over beers will be fun.
Yeah.
And we talk about this guy and about the Maltese stuff and all that. And we're building up some stuff. Yeah, I'm going to call the guy, okay? That's the thing.
Sure.
מה? כן. Come on. You think that you need a beer? He officially doesn't drink, but I think that he will drink after this. So, the Khufu, the jury,
The jury.
the international jury of your thesis has granted you with a 95. Yep.
Thank you.
Okay. So thank you. It was good. It was great. The comments.
Keep doing what you do because.
Yeah. There are several things that they are going to comment in the book that you need to.
I will send you the
that.
file. I will send Nicholas the file and then
Yeah.
see my comment.
Okay. Good. And thank you, Aaron, over there for the time and investment.
Thank you. Thank you for reviewing my thesis and the good comments for me. Thank you.
Goodbye.
And see you in a month.
Bye.
No? Okay,
Good.
that's it.
זהו, אני יכול לנתק?
Okay. Go for it. You did very good. His comments are already.
Thank you. Thank you.
His questions.
Now,
In questions, they were very good.
I have a
because-
question.
Yes,
No, it's
You know,
something
I asked the question because he asked it. Because actually, yes, you have uplift in Ethiopia. There is no reason why you won't see it in the Nile. Your question, you answer it. Your answer were good. A bit long, but it's okay. It's okay. It's in the context. If you answer a long, the more you answer, the more you can make mistakes. So you need to be. But it was okay. It was in the limits. Okay? But his comment on the Ethiopian plateau uprift is really good. I mean, you should. It may come in the paper.
Yeah, at the beginning, I read this paper.
You did?
Yes.
Okay.
No, I don't really buy that monsoon stuff. Why is that?
Yeah, she had a problem with the monsoon.
I have a problem with the monsoon. Why the monsoon? I'm not sure.
Maybe not only monsoon.
So be careful. You know, with this, it was a very strong statement. I wrote it down there. I wrote the problem with the tectonics that just made some changes in the tectonics and 1-2 meters, and you have channels or deep slope, a deeper slope, and more.
Maybe it becomes a work much larger. I don't know. If I talk about monsoon.
No, be careful. The less you say, is the better. But you already submitted the paper, so you don't have much to do now.
That's good for the.
I cannot. I presume you won't make many changes to what to your thesis because it's already submitted. Okay, these are my remarks. Just keep them in mind. And if you see that something doesn't fit